Okay, so let's start today's session. So this is the assignment for week 4 course. So in the previous 3 weeks we have done the previous year question and assignment and the detailed answers of that, but today we will do about the assignment for week number 4. So let's start. So in that question number 1, the kinetic energy of alpha particle in an alpha decay is 7.68 MeV. If Q value of the decay is 7.82 MeV, the mass of the parent nucleus is what? That is the question for the first one. Let me do just a minute. Can you see the screen, by the way? Can you see the screen? I think yes. Okay, fine. Okay, so coming to the first question, tells us about the kinetic energy of alpha particle. Let's say K alpha is 7.68 MeV. Okay, now they are asking about the what will be the if the Q value of the decay is 7.82 MeV, then what will be the value of mass of the parent nucleus? So let us assume the expression. Let's say I have the X, Z, A, right? Then it will give Z plus 1 A. Yes. Do you have anything to tell? If you have any problem, okay, fine. If you have anything to tell me, you can tell me right now. Okay. Then this is E minus, right? So this is a beta minus decay process, but they are asking about alpha decay. So what is alpha decay? Alpha decay is ZA, then it will go Z minus 2, A minus 4, and then helium 2, 4. Fine. So this is the alpha decay. So in that alpha decay, what will happen? Like they have given the alpha particle kinetic energy is 7.68 MeV, and the value of the Q value of this decay is 7.82 MeV. So in previous class we have already asked. We have the expression for the Q value and the kinetic energy relation. That means Q equals to E into 1 plus small m by divided by capital MD. What is these things? What are like? These are like, this is parent nucleus, this is daughter nucleus, and this is alpha particle, right? So the expression between Q value and this is the kinetic energy of alpha particle. So Q value and kinetic energy of alpha particle has the relation is like Q equals to K alpha into 1 plus, okay,
ma'am, you can continue, ma'am, please.
No, actually someone joined that, so that's why.
Yeah, please, okay.
Yeah, but fine. Okay, so here you can see that m is the mass of the alpha particle and md means the mass of the daughter particle, right? Daughter particle. So here we are talking about mass of alpha particle and mass of daughter particle. That means if I have a small m and capital M as well as capital E, then we can have the value of Q. But here in that question, what they have mentioned, they have already given E value, which is K alpha, and Q value is also given, and we all know that m of alpha is 4 because alpha is nothing but a helium nucleus, which is 2, 4. This is the expression for the alpha particle. So that means mass of a helium will, mass of alpha particle will be 4 always. So that means m alpha is 4. We have known that. So only the left unknown thing is this one, that is md, that is mass of the daughter particle. But in that question, what they are asking that mass of the parent nucleus. They are not asking about the mass of the daughter nucleus. If the mass of the daughter nucleus they are asking, then it will be md, but they are asking parent nucleus, that means mp will be nothing but md plus 4, because you can see here from the expression that here whatever the mass of the P, it will be I mean d plus 4, I mean md plus 4, because the alpha has 4 and md is a minus 4. That means md plus 4. So if in anyhow we can get the mass of daughter particle, then we can have the mass of parent particle from the daughter particle relation is like md plus 4. Fine. So just we have to just put the values of this one, and also alternatively we can write mp, as I already told that md plus 4. We can also write md equals to mp minus 4. So if I write the mp minus 4 and then this is md, then we can this is md and we are just replacing md by mp minus 4. Then what will happen here, you can see that 1 plus m alpha divided by md. So if I write that one md plus m alpha, so md plus m alpha means md plus 4 divided by md. So md plus 4 is nothing but mp, that is the mass of the parent nucleus, and this is mp minus 4. So as a whole this is coming like mp divided by mp minus 4, and there it is multiplied by t. T is nothing but the E, which is k alpha. Right. So now we have the value of k alpha, we have the value of q, we have the value of m alpha also, but we don't know about mp. So it's a very simple calculation. Then we can have the value of mp. So mp, the mass of the parent nucleus, and if I put all the values like q equals to 7.82, t equals to 7.68, and m alpha is 4, then the value of mp can be around 2 to 3.42. Now in that question they have mentioned that write integer value, because mass of the parent nucleus, write integer value. So so here you can see that the answer is coming out as 2 to 3.42. so which is nothing but 2 to 3, because it is like 0.42. we can have a approximation as we are getting the result in fraction and we need the result in integer number. So that's why it is like 2 to 3. Okay. Now coming to the second question, kinetic energy of alpha particle in an alpha decay is 8.30 MeV. Mass number of daughter particle is 201. What is the Q value of the decay? So here you can see that K alpha, which is nothing but T, which is also nothing but E, it is written as 8.30 MeV. Kinetic energy of alpha particle is given. Number of daughter particle, mass number of daughter particle is given. That means MD is given. MD is 201, and also we know that M alpha is 4. As per the previous question also. So if I put all the values, they are asking about the value of Q. So that means if I write all this, then Q value will be K alpha 1 plus M alpha divided by MD, right? So if I just put here 8.30, then 1 plus M alpha is 4 divided by 201, then what will be the value? This is the answer. Let me calculate this one. 4 divided by 201, this plus 1 into 8.30. So the answer will be 8.685, 465, sorry, 8.465. This is in MeV, because our K alpha was in MeV. You can see here. So our alpha particle kinetic energy is 8.30, and the mass of the daughter particle is already given. So what will be the mass of what will be the Q value for the decay? The Q value for the decay will be K alpha into 1 plus M alpha divided by MD, and MD is given as 201, M alpha is 4. So as a whole the expression is 8.30 into 1 plus 4 by 201, and it will be like 8.465 MeV. Okay, fine. So this is the second question. Okay, now coming to the third one, kinetic energy of alpha particle in the alpha decay. It's a very similar one. Kinetic energy of alpha particle in an alpha decay is 5 MeV. You can see here K alpha is 5 MeV. We have already written here. Now mass number of daughter particle is 98. That means MD is 98. Previously also it was daughter particle. Okay, so that means it's a very similar one. Then what is the value of Q1? Q is nothing but 1 plus 4 divided by 98, and E is here 5. So if I put all the values, then we can have the answer. So like let's say 4 divided by 98 plus 1 into 5.204. So it is 5.204. Now let's say I have one question here. Let's say our expression is like 1 plus m alpha divided by md, right? So let's say we in any question we have only the value of mp, and we have e value. Then they are asking for the q value. Then directly we can't put that mp value here because it is a md. So for that case, what we will do, we have to do mp equals to md plus 4. We will just convert this one, and after that we will put md as mp minus 4. So after putting these values, the q will be like 1 plus 4 divided by mp minus 4. Now here you can see that the mp is given here. So if the mp is like let's say it is 95, so if I put mp is 95, then 95 minus 4, then it will be 4 divided by 91, 1 plus, and then here it will be e. So this will be the answer of q. So like in any question, whenever the q will be asking or e will be asking, and also if we have md or mp, I mean in either of these two we can have the answer of q. Only we need one thing, we need the kinetic energy of alpha particle, and we need the mass of the daughter particle or mass of the parent particle, because both are interrelated. So if md is known, then we can have mp. If mp is known, then we can have md. And if it is e is also known, then we can have the value of q. I hope it's understandable by all of you. Okay.
Yes, ma'am.
Okay, thank you. Now coming to the second question and next question. In that next question, just wait for a minute.
Ma'am, is the meeting is being recorded?
Okay, so yeah, so in okay, ইন্টারনেট চলে গেছে। কি যাতা মাইরি হচ্ছে। এই এক্ষুনি গেল, আগে যায়নি, ভেবে দেখো তাহলে। দেখো তোমারটা দাও, তোমার হটস্পট দাও। রানা তো পাসওয়ার্ড দাও। ঠিক আছে। কই রে বাবা, এত স্লো। না গো, ফোনটা ওখানে আছে, তাও হচ্ছে না। ঠিক আছে, এসছে এবার। এসছে এসছে। হ্যালো হ্যালো। Okay. No, no.
Yes, ma'am. We are on the line.
Yeah, you are on the line, but I think my network is not stable.
Yeah. Okay.
Okay. Sorry. Just a minute. Just wait for a minute. Can you see the screen now?
Yes, ma'am. You can see.
Okay. Thank you. Okay, so just let's start. So
You can make it. Yeah.
It's fine, na? It's fine.
Yes, ma'am.
Okay. So in the beta,
Yes.
yeah. So just see the question. In the beta decay of SN127 to SP127, the maximum kinetic energy of the electrons emitted is found to be 3.2 MeV. If the atomic mass of SN127 is this one, the atomic mass of SB127 will be what? So, and you just see here the unit are different, like here one electron AMU unit is there for SN and the emitted electron kinetic energy is in MeV. So we have to convert these two in a single unit. That means if I can do U to MeV or MeV to U, so that the full expression will be consistent. Now coming to the expression here. So the question is asking about Ke, the kinetic energy of electron kinetic energy is 3.2 MeV. Fine. Now if the atomic mass of SN127 is 126.910360 U, and it is a beta decay. So beta decay means beta minus decay. Okay, so I'm just doing one calculation here so that you will understand very quickly that what is the answer, what will be the answer here. So you can see here that our Q will be the Q value has a very in general there is a very in general expression. The general expression is Q has the value Q equals to nuclear mass of what was that, SN127 minus nuclear mass of SB127 minus mass of E minus, right? So here in that expression, what is the given here? SN127, it will be SB127 plus electron. This is nothing but a beta decay, right? Like the beta decay means the SN can convert to SP and there will be one electron produced. So this is the expression for beta minus decay. So if I want to calculate the Q value for this expression, then Q value will be nuclear mass of SN minus nuclear mass of SB127 minus mass of electron. So but in that expression, in the question it is given that atomic mass of SN is given. So atomic mass of SN means, let's say I am writing here Z means, like it is not given here in the text question, so I am just writing here as Z. It will come as SBZ. It should not be Z because Z plus 1 it should be, because there is one electron. So for electron, you know that electron is minus 1 0, right? So the Q value in terms of atomic mass, what will be the in terms of atomic mass? If I write here mass of atom of SN127, then mass of atom means atom is consist of electron plus nucleus, right? So nucleus mass and electron mass as a whole, it is atomic mass. So in that question the atomic mass is given, but we want nuclear mass. So how we can have the nuclear mass? Nucleus mass is nothing but atomic mass minus electron mass. I mean how many electrons are there, so and each and every electron's mass will be subtracted from the atomic mass, so that we can have the nuclear mass. So this is okay, there is someone. Okay, so atomic mass minus electron mass should be there. That means a Z of, let's say, 0.511, because Z of the mass of electron is 0.511 MeV. So this whole is known as atomic mass, nuclear mass of SN127. Similarly, nuclear mass of SB127 will be what? SB127 minus Z plus 1 into Me minus Me. Can you hear me? Hello?
We are able to hear you, ma'am.
You lost your connector. आवाज चला गया था। चला से?
हाँ। तो इतना का वाइबर फॉस्फेट में इस विषय पे इंटरनेट है। हाँ तो
Just wait for a minute. Can you hear me? Hello?
तुम्हारे द्वार को चापे मोबाइल नेटवर्क में को बाजे नेटवर्क में
Hello? What?
ওইটা আমি এস বিশ্বাসের পাসওয়ার্ডটা ভুলে গেছি
ইন্টারনেট কি চলে এসছে? এস বিশ্বাস
কিন্তু পাসওয়ার্ডটা নেই না
দূর বাবা কারোর কাছে কি পাওয়া যাবে?
এস বিশ্বাস @123
সবগুলো ছোট হাতে?
হ্যাঁ
তোমারটাও তো এখনো হচ্ছে না। এস
বিশ্বাস @123
হয়ে যাবে বাবা, এত সময় লাগছে আমার। না, কেসটাকে বড় হাতের
কথাটা ভুলে গেছি আমি, শুধু বিশ্বাস দেন তুই আমারটা ইয়ে চেষ্টা করা
ওটা কার কাছ থেকে জানছিলে তুমি?
বিশ্বাস না আমি
হ্যাঁ,
নরেশের থেকে জেনেছিলাম, কিন্তু ওটা ঋতুর কাছে ফোন নাম্বারটা আছে।
আরে
তুই একটা কানেক্ট কর আমারটা।
যদি হয়ে গেছে তাহলে আমি সেখানে গিয়ে কানেক্ট করতে পারি।
হ্যাঁ
তাই
হয়ে
তো?
গেছে, আমাকে আমারটা ইন্টারনেট খুলছে।
ঠিক তো? ভগবান কি অবস্থা! কথা খুব হয়েছে। इधर उधर मैं घूम रही हूँ। क्लास हो गया था, बीच में बहुत भीड़ क्या है। Hello, can you hear me?
Yes,
That's
ma'am,
fine.
we can hear you.
Sorry, I'm really sorry.
No issues, ma'am.
Now I think it will be no problem. Let me check. Just a minute. I don't know why today the internet is that much fluctuating, but I hope it will be good right now. Can you see the screen?
Yes, ma'am,
Okay.
very clearly.
Okay, fine. So like,
That's fine.
yeah, so that question, did you hear anything or not?
Ma'am, just a minute, this is which assignment?
This is assignment number 4. You can see here.
Okay, ma'am.
Yeah. So the assignment
Okay,
number 4, I think you people did not hear anything on that assignment. So I'm just going to recap all these things a little bit quickly. Like I'm just going from the question number 4. Question number 1, 2, 3 has already done. So question number 4, I'm just going to tell again. Okay. I hope from right now the internet will be not that much problematic. Okay, so in that question number 4, what is the question? The question is like, in that there is a beta decay, and in that beta decay SN 127 to SB 127 is there, and they are telling that the kinetic energy of the electrons emitted will be 3.2 MeV. So if the atomic mass of SN 127 is this one, then what will be the atomic mass of SB 127? So I was just calculating a very general expression for the Q value, so that it will be applicable for all of the decays, because like this is beta decay. So beta decay means they are asking about beta minus decay, but after some questions we will also do the Q value for the beta plus decay. So what will be the in general expression for the beta decay and as well as the Q value expression, so that we can apply that Q value expression to beta plus, beta minus or electron capture, all of the experiment decay, right? So here I will just do some calculations. Just let me erase these things first, but I think I have space. No, I don't have space. So whatever I am going to write, this is a very general expression for the Q value, so that it will be applicable for beta plus, beta minus, electron capture, all of the 3 decays. So okay, so the Q value, this Q value has a 2 expression. First of all, what is the expression? The new mass of nucleus. I am writing here Mn as nuclear mass. Nuclear mass of parent particle minus nuclear mass of daughter particle. This is a very simple expression for Q value. So Mn is nuclear mass, P is for parent particle, D is for daughter particle or particles, whatever if there is two or more than two, all the particles will be called as D, and the MnD will be the daughter particle nuclear mass. Now if someone will ask about you atomic mass, let's say I am writing here atomic mass. So what is atomic mass? You know, like atom is made of nucleus plus electrons. So if I have Ma, that means it is Mn plus Me into Z. Z means like number of electrons in that atom. So Ma is Mn plus Me into Z. Me means the mass of electron. So if I write the Q expression in terms of Ma, then what will be the value? Mn is Ma minus Zme. So Mn is Ma minus Me into Z minus similarly Ma for P and here Mn for D. Mn for D minus Me of Z prime. Why Z prime? Let's say for daughter particle the Z prime electrons are present in the daughter particle. So Me into Z prime will be the mass of the total electrons for that daughter particle. So someone has come. So do you understand this one? Like here Ma minus P, MAP minus of Z into Me minus as a whole MnD minus Z into Me. This will be the final answer, right, for the Q, and it will be in terms of atomic mass. If there is a nuclear mass, then nuclear mass is there, that means nuclear mass of parent nucleus minus nuclear mass of daughter nucleus will be fine. But if atomic mass is given, that means we have to subtract the atomic mass from the mass of the total electrons, whatever it is present in the atom. So now you can see that in that question it is saying that atomic mass of Sn is given. So what will be the atomic mass of Sb127? That means you can see here, let's say I have here they are not mentioning about Z value. You can see here there is nothing as Z value. So we don't know what is the Z value for that Sn. That is fine. We don't want to know that. So what we will do? We will do like Z plus 1, 127. Obviously it should be Z plus 1 because there will be 1 electron out. So that means Z plus 1 minus 1 which will be Z. And 127, 0, 127. So in terms of atomic mass, they are given as atomic mass. So that means our Q will be in terms of atomic mass. So if I write here Q in terms of atomic mass, then what will be the value? Ma for Sn minus Me into Z minus, what will be in minus? All the things, whatever the product particles are there, for that the in between of this. So Sb, that means Ma of Sb minus Me into Z plus 1, because you can see that this is Z plus 1. So these two are nothing but as a whole it is a Mn of Sb. Fine. Now also what is there? This is Me of E, because it is only 1. Sorry, it should be 1 because there is only 1 electron. 1. Okay. So this will be the expression in terms of atomic mass. So here Q value is already given. I think Q value is given, right? Yeah, Q value is 3.2. So Q value is given and Ma Sn is also given. and so we have to calculate MASB. So how can I calculate this one? Okay, now come to that part where to write. Just I'm just going to write here. So here you can see that Q equals to, wait, okay, so Q is already given 3.2. Now MASN is already given. MASN is 126.910 something. So 126.910360, and it is in AMU unit. That means you have to convert that in MeV. So 931.5. So as a whole, this is in MeV. Now there is this one. So what will be the value? ME into Z minus MASB plus, because minus is there, that means plus Z plus 1 into ME. Now it is minus again. Fine. Now if I just a little bit calculate this one, then you can see that MZE, this is MZ into E, and there is, okay, this is minus, right, minus MZE, and then ZME plus ME minus ME. That means as a whole these four terms will cancel out. Then what will left? Only this term will left. So the left answer is 3.2 equals to 9 something 126. Yes, 126.3. What was that? 91036 into 931.5 minus MA of SB. So from that we can simply calculate the value of MASB. MASB is nothing but 3.2. Oh sorry, I mean as a whole this minus 3.2. So if I just calculate a little bit, then it will be like let's say I am calculating here 126.91036 into 931.5. This minus 3.2. This will be in MeV. Now you can see here the result is in unit. So that means that should be divided by 931.5. You can see 126.9069 2461 means obviously it can be like 25. Then this will be the correct answer, 126.906925. Do you got my point? I think it's understandable, right? Can anyone?
Yes ma'am, yes ma'am.
Okay. So
actually either we can convert that atomic mass unit into MeV, or that 3.2 we can convert into atomic mass unit, and we can subtract from 126.910360. So the same answer will come.
Yes, obviously, because like one is in AMU unit and another one is in MEV unit.
Yes.
So we have to convert either this one to here or this one to here. I mean anything.
The answer is 126.906925.
Yeah, like here you can see that here whatever we have calculated here right now, it is like 126.90692468 to 2468 means obviously we can take it to 5. That is.
Yes ma'am.
Yeah.
Thank you.
So that's why the correct answer is A. Now coming to the next question, so that you can understand that what is the difference I was talking about. You can see here in the beta decay of Tc99 Ru99, the maximum kinetic energy of the electrons emitted is found to be this one. If the atomic mass of rubidium is this one, the atomic mass of this one is what? So it's a very similar to whatever we have learned just right now. So what will be this? The Q value will be, see, it is also given that atomic mass. So if it is atomic mass, then obviously we have to write the atomic mass, and it is also a beta plus T, a beta minus Tk. Okay, so in beta minus Tk, the expression of atomic mass unit, in atomic mass, the expression will be like Ma of Ru, sorry, Tc, Ma of Tc minus Ma of Ru. That will be the expression, simple expression, because you can see that previously also we calculated that mz, whatever these things were there, that will be cancelled out, because Me into Z and then Z plus 1 into Me, and then it will be again Me. So you can see that Me Z plus 1 will be cancelled out, and minus Me plus Me will cancel out. That means the atomic mass will be, the Q value will be Ma of Tc minus Ma of Ru. So Q is here 4.89. It is in MeV. So here MATC we have to know. Okay, MATC we have to know. So MARU is given. MARU is 99.9987. There are too many numbers. Then it should be multiplied by 931.5. Or whatever he told that you can convert that one in U, and after that you can multiply, subtract. That is also possible. So that what will be the answer? Then MATC will be nothing but 4.89 plus as a whole into 931.5. This will be in which unit? This will be in MeV unit. Okay, so now what we will do? We will just do like this into 931.5 divided by 931.5. This will be the answer. So let's just calculate that answer. It is like 4.89 divided by 931.5. This one plus, what is the
that atomic mass unit we can directly add.
Yes, 99 point something 998736. So that is 100.3985. So that means the TC is 100 something 0039875. So 0039. So this is in E. This is in U unit. Okay. So I think you have 0.0039 U. That will be the atomic mass for TC99. Okay, good. Now in that next question, where is that beta plus? Just a minute. There is one beta plus also there. Okay, I think I removed that part. This one, yes. Okay, now see this one. The atomic masses of Rn 86205 and AT 85205 are this one and this one respectively. The Q factor of the beta plus process. So here beta plus process is given. So they are asking that what will be the Q value for that beta plus. So that there is a little bit tricky thing. So what is the tricky thing? I have already told that they have, okay, so these are the atomic masses, whatever they are given, these are the atomic masses, you can see here. So atomic masses means, as we have already told, that atomic masses should be written in terms of nuclear masses, because the general expression was nuclear mass of parent minus nuclear mass of daughter, right? So in that beta plus process, first of all I just want to write the beta plus process. Beta plus process, what will be happen? 86205, then it will go as 85205, then E plus. Why E plus? E plus is nothing but 10. Then you can see that 85 plus 1, that is 86, and 205 plus 0, 205. Fine. So this is the beta plus process. Now in that beta plus process, what will be the value of Q in terms of atomic mass? First of all, we want to calculate in terms of nuclear mass. So what will be the value of nuclear mass? The nuclear mass is very simple, Rn minus Mn of At minus M of E. See, M of E, why I am writing here, sorry, this will be 1, because there is only one electron. I mean positron is there, but still positron mass and electron mass are same, so that's why we are writing here Me into 1. Now this is in nuclear mass. Now we have to convert the nucleus mass in atomic mass. So for atomic mass of Rn, what will be the value? Mn of Rn plus Me into Z. So what is Z for Rn? Rn has Z as 86. That means Mn of Rn plus 86 into Me. So this is the MaRn. Okay. Now coming to the Ma-At, atomic mass of At. So what will be the value? Mn-At plus Me into, what is the Z for At? 85. 85. Fine. Now I have to write Q value. So in that Q value you can see that MnRn. So MnRn should be replaced by MaRn minus 86 into Me. So MaRn minus 86 into Me minus Mn-At. Mn-At means Ma-At minus 85 into Me. Again there is one minus, you can see here minus Me, that means 1 Me. So this will be the expression. So what will be the final expression? Minus Ma-At, I am just going to side change. Then you can see here that minus 86 Me, then this is minus minus plus 85 Me, again minus Me. So as a whole what will be the result? The result will be like minus 86 Me and then it is 85, that means as a whole minus Me, and again minus Me, that means 2 Me. So it is not like that. I mean you can see that for beta minus decay, there was only MaRn minus Ma-At, but for beta plus decay it is MaRn minus Ma-At minus 2 into Me. So you should remember these expressions, okay, because they are giving atomic mass. If they will give nuclear mass, then there is no need of minus anything. But if they are giving the atomic mass, then you have to consider this part, that MaRn minus Ma-At minus of 2 into Me. So you can see here I have written here M of Rn, M of At minus 2 into Me. Now you just write here 204, whatever the values are there. Then Me is 0.55. So 0.55 MeV is there. So we have to convert that MeV to U. Now we have to calculate this one, and if you want, then you can calculate in MEV also. Then correct answer is B, 4.24. Do you understand the point? I think yes.
Yes, ma'am.
Okay.
The answer is 4.24, right?
Yes, 4.24. Because see, this is the main thing, that you have to subtract here 2Me. That is the main thing for beta plus decay. But in beta minus decay, you don't need to subtract anything. That is the thing. Okay, now come to the next question. What is next question? Okay, the atomic masses of Mg and Na are this. The Q factor of beta plus process is what? It's a very similar one, whatever we have done in the previously. So just quickly do that one. Let's say Q. As we have told that see here also it is mentioned that atomic masses. That means Ma Mg minus Ma Na minus 2 into Me. So just we have to calculate the values like 23.98504 minus 23.87304 minus 2 into 0.511 divided by 931.5. Then I have to calculate this one. Then I think something 0.511 divided by 931.5 into 2. Now 23.98504 minus 23.87304 minus this one. This is 0.1109. This is in Okay, this is in MeV. Yes, no, this is in U unit. So if you want to calculate this in MeV, then what you have to do, see, 1 U is 931.5 MeV. Okay. So if you convert that, then 1 MeV will be 1 by 931.5 U. So whatever the answer is, if you have to just divide that one by 931.5, then this is the answer. Whatever the answer will be, that will be the Q value. Okay, I think it's understandable.
Actually, we have to divide or we have to multiply the last one, atomic mass unit into 931, right? Not the divide.
Okay, let me check that one. Just a minute. See, yeah. So here you, okay, you have to multiply. Sorry, because the U is there. Like, what was the answer? Something 0.
It was 0.11 something.
0.1101. So after that 931.5.
11090.
Yes, like that.
Yeah. So it is 103.306 something.
Yes, because like it is the conversion is like 1 U equals to 931.5 MeV. So we have to calculate in MeV. Like we have already calculated in U unit. So if you want to calculate in MeV unit, then you have to just multiply with 931.5. Good. Okay. Yeah. So now coming to the next question. This next question is little bit different from whatever we have done previously. So what is the next question? The next question is, consider the beta decay. K46, IP is 2 minus, and it will go as calcium 46, IP is 0 plus beta minus. Is this an allowed or forbidden decay? I mean, the first question is that one, and the second question is it Fermi type or Gamoteller type? Like, there are two questions. First of all, they are asking that whatever we have taken as an expression of beta decay, is that expression is allowed or forbidden? That is the first question. And the second question is, if it is allowed or if it is forbidden, then that is fine, but which type of decay it is? Is it Fermi type or it is Gamoteller type? So I hope these terms are not fully new for you people, because in that week number 4, I think sir has already told about what is Fermi type beta decay or Gamoteller type beta decay. So I have one plot here. Okay, this is a table for that Fermi and Gamoteller type expressions of beta decay. Then how can you understand that any beta decay is, which one is Gamoteller or which one is Fermi decay? So for that I have made an condition like table. You can see here that first of all I have written here transition. So transition will be allowed in some specific condition. Transition will be first forbidden in some specific condition for Fermi decay as well as for Gamoteller decay. So in the Fermi decay, you can see here Fermi rules. In the Fermi rules, delta I will be 0 for allowed transition, and the delta I will be 0 or plus minus 1 except 0 to 0. This condition will be for first forbidden for Fermi type beta decay. Now also again you have to fulfill the second condition of Fermi rule. The second condition of Fermi rule is parity change. There should not be any parity change in the allowed transition of Fermi type beta decay, but there should be one parity change in first forbidden transition in Fermi type beta decay. Similarly, you can see here that for Gamoteller the transitions are like that: yes, no, no, yes, and then the conditions are here. Now I just want to explain you this table in respect of this condition. I mean the example. Whatever the question was, just write the question whatever it was. Let's say 46, then calcium.
Can you please show the table once again?
Yes, sure. This is the table.
Yeah. No, yes. Okay, okay, thank you.
Okay, so like we will discuss that one, but right now at the very first we have to write that one. Yes, see here K46, then it will come as calcium 46 plus beta minus. This is the beta decay. So first of all we have to see that this beta decay is allowed or not. So let us write here IP value. So what is the IP value for that? It is already given here. You can see here 2 minus, then 0 plus, and there is nothing. Okay, why nothing? I will tell that, but before that you can see here I minus is 2 minus for IP is 2 minus for K, and IP is 0 plus for calcium 46. Now coming to the table, IP potassium, this is calcium, this is 2 minus, this is 0 what 0 plus. Okay, 0 plus. So first of all we have to consider the I value. So at the very first I1 was 2, I2 is 0. That means what is the delta I value? Delta I value is 2, which is not equals to 0. That is obviously correct, because delta equals to 2, which is not equals to 0. That means this condition will not be fulfilled at the very first, because you can see that delta I should be 0 for Fermi rule of beta decay in the allowed transition. So that condition has already gone. Now coming to this condition also you can see that 0 plus minus 1. So that means I have delta I equals to 2. So it is also not correct. There you can see that 0 plus minus 1, that also not correct. Here you can see that 0 plus minus 1 is plus minus 2. That means this condition can be right, can be. Okay, because delta equals to 2. Now coming to the parity change, you can see here parity. What is the parity here? That one was minus, this one is plus. So parity is changes or not? Obviously parity changes, because previously it was negative, now it is positive. So parity change is yes. That means you can see it was a little bit cut, but still you can see here it was parity change basically, right? So the parity change for Gramotalar rules is yes. That means these two conditions are already satisfied. So what is this? What will be the answer for the question? The answer for the question will be the beta decay is gamotalar and the transition will be first forbidden. So the answer will be first forbidden and then it is a gamotalar transition. Fine, na?
Ma'am, a small doubt.
Yes.
Ma'am, suppose if the initial state was 3 plus and
just
the
a
final
minute.
state was 0 plus, then in that case delta I will be 3. So according to this table, in which kind of transition it will be, ma'am?
Okay, just a minute. I was just admitting. Okay,
Because
can you tell
only
me?
we are having 0 plus minus 1 plus minus 2.
No.
Suppose if delta is greater than 2.
Okay, delta I is greater than 2. Obviously that type of... Yeah. I mean, if it is greater than 2 means 3, 4, 5, whatever. That type
Yes,
of...
yes.
Yes. So for that type of beta decay, it obviously not possible. There will be no first forbidden, second forbidden, nothing will be there. Simply it is not possible. Only delta I up to 2 is possible. But possible in which sense we have to see that. Is it allowed? Is it first forbidden? Is it second forbidden? That we can see. But delta 2 greater than 2 is not possible anyhow. Okay. I have one question regarding on that also. I will tell that this section also. Okay. So the answer is D, right? Yes, the answer is forbidden gamotalar. Now you can see once also. See, let's say you can see here that Fermi rule is 0 here also 0. Then how can we understand that if 0 is there, then which one will be the correct one? Obviously there is another exception is there. 0 to 0 will not be acceptable here for the first forbidden. You can see here. So let's say I have 0 plus to 0 plus. Then delta I equals to 0. So this delta I equals to 0 will not be corresponding in this case, because it is written here that except 0 to 0. Then that delta equals to 0 will be considered here. And also here you can see that the parity will also be considered. Obviously the parity will also be satisfied here. So 0 plus 0 plus means parity is no change. That means this 0 plus is nothing but Fermi rule allowed. I mean Fermi type beta decay will be there and the allowed transition will be there. So this type of things. Okay, I will tell in the next question also in detail, not this one. Okay, let me just go there so that we will understand quickly. Yes, consider the beta decay here. XA IP equals to 0 minus, YA IP equals to 0 minus plus beta minus. Very simply we can see. So here I don't know what is X, what is A, I don't know what is Y, what is A, I don't know anything, but no problem, we just want to know the value of IP and IP. So here you can see that XP, then XA, YA. Then what is this one? 0 minus, 0 minus. You can see here delta is what? Delta is 0 because there is no change. 0, 0. That means delta is 0. Now coming to the p value. So p value is changes or what? It is not changing because previously it was negative, right now also it is negative. Then we have to come to the table that delta I in which condition delta I is 0 and delta p is no change. So just go to that table so that we can understand. Delta I is 0 and parity is no change. That means which one will be the correct answer? Allowed transition will be there and it will be Fermi type. Yes. So here this one will be the correct one. Do you understand the point? Because it is 0 minus, 0 minus. Okay. Now coming to the next one. Let's say I am giving one example to you people. At the very first IP was 0 minus, then the next, the product one has the IP as 1 plus. Then what will be the condition? Like will it be the allowed transition or it will be the forbidden transition? If it is allowed, then which type of, or if it is forbidden, then which type of? Then yeah. Okay, then calculate just here delta I. Delta is what? 1. And what is delta P? Delta is yes. In according to our table it is yes and delta I equals to 1. So just go to the table so that you can understand. Yes. So here there is so many things. Let me calculate, erase these things. So here
it will be first forbidden and Fermi.
Yes, and then first forbidden. Right. Now you can also see that here also ZT is 0 and yes. This condition is also satisfied, right? But here they are asking about 0 to 1 is exception. Except 0 to 1. But in our case what was there? In our case was like 0 to 1. See, this 0 to 1 it can also, I had 0 minus 1 plus or something. So you can see that delta I equals to 1 and parity is yes. So these two condition is also satisfied here. Delta I equals to 1 and parity is yes. But we can't have GT rule because there is already written as the exception is 0 to 1. You understand? I think you understand that one. But let's say I have 2 plus 2, 3 minus. Now what will be the type? 2 plus 2, 3 minus or 4 minus. 4 minus will be good. 2 plus 2, 3, 4 minus. Then delta I equals to 2 and parity is yes. Then obviously it will be a gamoteller and the first forbidden region will be there. Okay, I think it's understandable. Okay, now coming to the last question. Just see the last question. It's a little bit tricky question, so that's why I need a little bit more time on that. So in that last question, what is the question? The atomic masses of a xenon 54 136. It has IP value 0 plus. CS 55 136. It has IP value 5 plus. And barium 56 136. It has IP value 0 plus. These all three has the atomic masses this and this respectively. They are already given. Now the question is, which of the following statements are correct? Okay. So okay, there are four conditions. First condition is the single beta decay of xenon is not energetically favored. I mean, there are so many questions, so there are so many options. It may be possible that among the four options, one or two can be correct. It's a multiple choice and that MSQ type question. So we have to check each and every answer so that we can conclude which one will be correct one and which answers will be the correct one. Okay, now let me just first write the expression so that it will be understandable. 136 54 CS 55 136 BA 56 136. Now you can see here that 54 55 56. That means if the beta decay is possible, then beta decay means from here to here beta decay is not possible. I mean, only one single beta decay is never possible from xenon to barium. Correct? Can you hear me?
Yes, ma'am, we can hear you.
Okay. Yeah, just a minute. Yes, tell me. Yeah, I am just asking that from xenon to barium only one single beta decay is possible or not? Simply not possible, because in one beta decay at least M54 can go to 55, not 56. That is the first condition, right? It's final. That xenon cannot go to barium in one single beta decay. Okay. Now come to the condition that CS can go to BA. That can possible in one single beta decay. But it can also be possible xenon can go to barium in double beta decay. In double beta decay you can see double beta decay means 54 will go to 55, then 55 will go to 56. That is possible. So in double beta decay xenon can go to barium, but in single beta decay CS can go to barium. That is the condition. Okay, this is the very simple one. Now coming to these things, this mass. Because see here in that question they have given so many things as a whole. What they are given? They have given ZA value for each and every particle. They have given the mass of that particle. They have given the IB value of this one. Right? They have given three things in one question. So we have to yes. So we have to understand this one very carefully. Barium 56. Now I am just going to write the mass of this 135.90722, then 135.90731, 135.90731, and this one is 4458, 135.90458, I think, yes, 458. And let me write here again the IP value 0 plus 5 plus 0 plus. Okay, 0 plus 5 plus 0 plus. As someone asked me right now that if what will happen if delta is greater than 0, greater than 2. I told that if delta is greater than 2, that means our decay will not be possible. So you can see here that xenon to cesium, what is that one? Delta I equals to 5 here. So obviously xenon cannot go to cesium. That is a very 100% sure possibility. So that means that xenon cannot go to CS. That is the first one condition. Xenon cannot go to barium with one single beta decay. Cesium can go to barium. That is the things. Okay. Now coming to the energy. See, mass is nothing but related to energy. So beta decay will only be possible if and only if delta Q will be positive. What is the meaning of delta Q will be positive? Delta Q will be positive means xenon, let's say I am writing xenon is going to cesium, then the mass of xenon should be greater than mass of cesium. But in that case xenon is not going to cesium because of the delta E greater than 5. Okay, so now I mean you understand the things that we have to consider step by step. We have to first consider that Z value 54, 55, 56. Now we have to consider the mass number, which one has the greater mass from which, and after that we have to consider IP values. These are the things. Okay. So now coming to the first condition. What was the first condition? The single beta decay of xenon is not energetically favored. They are telling like that. This is single beta decay of xenon. So the single beta decay of xenon means single beta decay means obviously xenon should have cesium. But they are saying that single beta decay of xenon is not energetically favored. So let us first see what is the energetically favored thing. Energetically favored means our delta Q should be greater than 0. So what is delta Q here? 135.90722 and 135.90731. So you can see here that for delta Q greater than 0, our mass of xenon should be greater than mass of CS. Is it like that? Is the mass of xenon is greater than mass of cesium? No, because the mass of xenon is like 722 and here mass of cesium is 731. That means it is not energetically allowed. So this xenon to cesium is not energetically allowed beta decay, and also it is not allowed by the expression of IP. But whatever they have mentioned here, the single beta decay of xenon is not energetically favored. That means the statement whatever written in option number A is correct. Do you got the point? See, like there are so many things in one question, so that's why I am just going very much slowly.
Yes, ma'am.
Okay.
So here we have not mentioned that change of pair.
No.
That is spin also, right?
Yes, because whatever they are asking, I will go like that. They are asking that it is energetically favored or not. Obviously, it is not energetically favored because delta Q is less than 0. Okay, fine. Now coming to the B option. What is B option? The single beta decay of xenon is energetically favored but is highly forbidden, involving large orbital angular momentum of the electron neutrino system. See, the difference between A and B is like they have in option number A they are talking about that it is not energetically favored, but in the second option they are talking that it is energetically favored. So obviously it will be wrong, but we don't need to see these portions, because as we have already proved that equation option number A is correct, obviously option number B will not be correct. Okay, now come to the third option. Double beta decay of xenon is an allowed reaction which is energetically favored. That means they are telling that double beta decay of xenon is allowed reaction and as well as it is energetically favored also. Now coming to the double beta decay. Double beta decay. So in that double beta decay, what is there? Xenon will go to barium. Yes. Xenon will go to barium. So what will be the mass? 135.90722 and it is 135.90458. Now can you tell me, is it energetically favored or not? What will be the value of delta Q?
Energetically favored, ma'am. The Q value is 2.45916 MeV.
Yeah, like
it is greater than.
Yes, whatever it is, it is greater than 0. That is the main thing. So it is positive value and it is greater than 0. That means it is energetically favored. Okay, fine.
Yes.
Okay. Now what they are telling, it is an allowed reaction or not, that we have to check. Which is energetically favored, that is good. But it is an allowed reaction or not, we have to check that one. How can we check that? With the help of IP value. Okay. So what was the IP value for xenon? It was 0 plus. And what was barium? 0 plus. That means 0 plus will go to 0 plus. So what will be the delta I value? Delta I value will be 0. What will be the parity? Parity change is no, because positive to positive. Now coming to the table. Yeah. Yes, now coming to the table. Table means delta equals to 0, parity change is no. That means this condition will be satisfied. And what is this one? This is allowed transition. So whatever it was in that option, yes, double beta decay of xenon is an allowed reaction which is energetically favored. So these two are exactly correct. It is also an allowed reaction, it is also an energetically favored reaction. That means the option number C will be correct. Okay. Now coming to the fourth one, double beta decay of xenon is energetically favored but is forbidden considering orbital angular momentum. As we have already seen that it is allowed reaction, so yeah, so this is also not correct because it is written that it is forbidden considering orbital angular momentum. So this option will not be correct here. So the correct answer will be A and C. Okay, fine. Yeah. So the correct answer is A and C. Okay, I think I have done I have done full week 4. So these are the questions. So if you have any doubt, you can ask me on this topic. I am just going through thoroughly. Yes.
Ma'am, is it possible to have what do you call as recorded version of this video, because some of the students may have missed it?
Yeah, and obviously there was a too much fluctuation in network today, so
Okay.
yeah, so I have recorded that one, no problem. I have recorded that one. I will send
What about the previous 3 weeks solution
Yeah.
sessions now?
Okay, so it has already there in YouTube. If you just search in YouTube, you can get all the videos there. Okay, just I am going to see that. See here, just you write YouTube, then write, you all know what is YouTube. So you have to just write here my name. If you just write my name, then you can see that week 3 previous year assignment nuclear particle physics. It was 4 days ago, right? And after that week 2 is there, and I mean all the things are there. Week 2, week 0, week 1, week I mean all the weeks are there. And right now today it will be week 4.
Yes, ma'am. Thank you, ma'am.
Okay, so, and otherwise there is like maybe NPTEL coordinator will give you some link. Through that link also you can have the access to see these videos. So yeah, so
Go to the problem number 2.
okay, problem number 2. Yeah.
Okay, problem number 3, ma'am.
Yeah.
Like that you can show, because some of the students came
Yes, I understand. From the very beginning I am just seeing that one, so that each and everyone can see the question as well as the answers also. My handwriting is not that much good, so just see the question. These are the question.
Ma'am?
Okay. Yes.
Hello, ma'am.
Yes.
Ma'am, in the assignment we had been given one problem like the parent nucleus is in 3 plus state, spin state,
Okay. Just a
and the
minute.
daughter is in 0 plus state.
Daughter
It's a
is
beta minus decay.
No, it will not be possible.
Ma'am, in the options we are given,
Huh?
ma'am, but in the options we are given allowed Fermi, forbidden Fermi, allowed Gamow-Taylor, forbidden Gamow-Taylor. So which option we have to mark? Because your delta I is 3 and no change in parity state.
If it is delta I equals to 3, obviously there should not be any option. Like among these 4 options, there should not be any option. But I have to check. Like, is it the answer? Is it the correct question you are talking, or?
Yes, ma'am. It is assignment number 4, question number 5, ma'am. Consider the beta decay. 26 Na bracket 3 plus spin state to converting to 26 magnesium bracket 0 plus spin state and plus beta minus particle is emitted.
And beta minus does not have anything IP, right?
No, ma'am. No.
Yeah. So
They have not mentioned anything.
So it
But
should
the
not.
options are given 4 options, ma'am. Allowed Fermi, forbidden Fermi, allowed Gamow-Taylor, forbidden Gamow-Taylor.
Yeah. So for that case, as per I know, there should not be any of that answer, because like as you can see from that table, where is that table? Yeah, you can see here that from table it is up to plus minus 2, and yeah, if there is, okay, so the things are like, if it is delta I greater than 0, that means there will be no allowed, no first forbidden. Either it is Fermi type or it is Gamoteller type, there will be nothing on that allowed and first forbidden. But maybe there is some mistake in that question, so if there is like that, then I will see the question and after that I will inform to sir,
Okay.
so that change or
It is assignment number 4, question number 5, ma'am.
yeah, I understand. See, like for my case, like I will not tell the answer of that current assignment, obviously, because current assignment means you have to do that
yes,
one.
Yes, ma'am, you are correct.
Yeah.
But even I too felt that this value, this change of delta I doesn't fit in the table.
Yes, I understand.
That is why I asked you, ma'am.
Yeah, I understand.
I know, ma'am, I'm not expected to know the answer from you.
Yes.
I very well know that fact. But since I read so many YouTubes regarding this, but nowhere this delta I.
Yes. So delta I should not be greater than 2.
Yeah. But here it is coming out 3, and even they have not given whether it is double decay or super 3, ma'am. Oh,
Yes.
That is why I asked it.
Yeah, I understand.
Because in one of the YouTube videos, I thought they have given it may be super allowed for me.
I understand your point. So as it is the
Yes,
four
yes,
options,
yes, ma'am.
the 4 options are like that, I think, right? Whatever it is given.
Yes, ma'am.
So exactly these 4 options were there. So obviously if it is, so if these 4 options are given there, so that means delta I should be less than or equal to 2, so that the answer will be there. So
Exactly.
yeah, so I will talk to sir and after that I will let you know. Okay, so just
Ma'am,
first,
very nice class, ma'am. Very nice, ma'am. So much insight, ma'am. Thank you so much, ma'am.
Yeah,
Very
thank
nice.
you.
So many concepts are cleared, ma'am.
Thank
Very happy,
you.
ma'am. First time I am listening to this, ma'am. I'm very happy, ma'am.
Then you have to join each and every class.
Yes, ma'am. Definitely, ma'am. I will join, ma'am. Very nice of you, ma'am. Very nice of you.
Okay, now see the first question and second questions. So this is first question. Okay. See, basically, from the very beginning of my today's class, there was too much internet fluctuation. So, whoever did not join the class, just see the questions right now. Then, if you have any doubt, you can just ask me. This is the first question. Now.
Ma'am, these videos are available, no, ma'am,
Yes.
on YouTube?
Yes.
Thank you. Thank you.
So after the class, I will upload the video within 1 or 2. After 1 or 2 hours, I will upload, and after that you can see that.
Okay. Thank you.
So this is question number 2. Now come to the question number 3. This is question number 3. See, I have written here so many questions very similarly. Like question number 1, 2, 3 are very similar. But just to understand very little bit clear, I have just written that one. Then question number 4 is this one. Question number 4. Then question number 5. Then question number 6. And also in your recent assignment, I have seen that whatever I have taught in that class, today's class, these questions, I mean, very similar to that questions were there, but also there are new type of questions were also present there. So like that type of question I could not answer because they have already mentioned as a current year assignment. So among these questions, if you have any doubt after completing that, there was, I think, 20th August is the last date for submitting of the assignment 4, I guess. I forgot the date at which. 23. Okay.
23, ma'am.
23.
Okay, so after 23, if you have any doubt on that question number, week number 4 assignment on the current year, then you can ask. Not right now, it will be after 23. Okay, so that I can so that I can answer on that question, because I could not add this type of question here as it is already mentioned in the current year assignment. Okay, then question number 7 it is. Now Question number 8. This is Fermi type and Gamma-Taylor type. Then question number 9. This 9 question is a very good question as far I understand. Like, for my opinion, it is a very good question because you can see that in only one question there are 3 things we have to mention. We have to consider 3 questions so that it will be very good at least. Then question number 10 is very similar to that Fermi type and Gamma-Taylor type, and it's done. So I hope it's already understandable by all of you.
Thank you, ma'am. Yes, ma'am.
Okay, so today's class we can stop here, and I will share the PPTs also here. The PPTs also will be shared to you, I think. So like I will share in a Dropbox, and this Dropbox will be like it will be shared by the NPTEL coordinator, I think 1 or 2 weeks later. So you can also see that PPTs whatever I have written here. Okay, then just that much is for today's session, and we will meet in there is one I think next Sunday I will not be here, so I will not take the class in next Sunday. The class will be on the class will be on 2nd September. The class will be on 2nd September because I will not be available here, so that's why. And on 2nd September week number 5 will be discussed. Okay.
Actually there will be another set of assignments we should submit on 30th of August, right?
30th of August 5.
Yeah, week number 5 assignment we have to submit on 30th of August.
Okay, but sorry for that because I will not be here for 1 week, so that's why I will not be join on that date. See, basically for my case, my classes are on each and every Sunday, but this Sunday I will not be here, so that's why I have shifted my class on Friday today. So for that next class means 27th August will be there, but 27th August also I will not be here. So that's why like I have just changed, I have shifted my class on that next Saturday, that 2nd September. If you see the calendar, then you can see that 2nd September is Saturday. So that means on that Saturday I will have the class, and again on 3rd September, which is very general, which is very similar on that each and every Sunday class, that I will take. So that means on 2nd September week 5 I will discuss, and on 3rd September I will discuss about 6th week. So it is like as I will not be available here, so that's why only it will be a little bit mess up. 2nd September will be the 5th question, week 5, and the 3rd September will be on week 6. That is the thing.
Okay, ma'am. Thank you, ma'am.
Yeah.
Thank you.
Okay. Ma'am, thank you, ma'am. Thank you so much.
Okay, thank you. Bye-bye.
Bye, ma'am.